Today, I'm going to prove without any calculus that the second derivative of any quadratic function is constant. And specifically, we're going to show that the second derivative of a function of the form ax squared plus bx plus c, classic quadratic function, is 2a. So to answer the question, why do quadratic functions have constant second derivatives, you need to know what a second derivative is and what a quadratic function is. And I'm assuming most of you already know that, so I'm going to put timestamps below if you want to skip this part. But just in case you don't, I'm going to show you what a second derivative is. And I'm going to show you entirely via an example. So let's say you have some population that's growing. Population grows by more and more every year. So x could be our years, and y could be our population. Okay. And let's say in year 1, the population is 100. In year 2, it's 110. Year 3, it's 125. And year 4, it would be 145. And year 5, it's 170. So first, between year 1 and year 2, the population increased by 10. Between year 2 and year 3, it grew by 15. Year 3 and year 4, it grew by 20. And year 4 and year 5, it increased by 25. This right here, 10, 15, 20, 25, this is the regular derivative. It's the first derivative. First derivative describes the rate of change of the population. But notice here, the rate of change itself isn't constant. It's growing by more and more every year. So between, for example, year 2 and year 3, this rate of change went up by 5. And then here, between these 2 years, it went up by 5 again. And then our rate of change went up by 5 again. So this plus 5, this is the second derivative. It's the rate of change of the rate of change. If this were speed, this might be acceleration. That's what a second derivative is. And because the second derivative is always 5, that means the second derivative is constant. Now that you hopefully have some kind of intuitive understanding of what a second derivative is, we're going to try to prove that all quadratic functions have a constant second derivative. So quadratic function, basically, if you don't remember, is any function of the form ax squared plus bx plus c equals some y, where a, b, and c could be any numbers. So a could be 3, b could be 2, c could be -5. That would be a quadratic. And the most basic form of a quadratic is the quadratic where b is 0 and c is 0 and a is 1. So it's just x squared equals y. That's the most basic quadratic function. So does this basic quadratic function have a constant second derivative? Well, we can set up our table again. And x equals 1. X squared is going to equal 1. When x equals 2, x squared equals 4. X equals 3 equals 9. 16. So here, when x changes from 1 to 2, the y goes up by 3. When x changes from 2 to 3, the y goes up by 5. And when x changes from 3 to 4, the y value goes up by 7. And this is the first derivative. This is the rate of change. So the second derivative is how fast this rate of change is going up. Well, first it goes up by 2 more. Then it goes up by 2 more again. If we were to expand this out, the difference between 16 and 25 is 9. So it goes up by 2 again. It certainly looks like it has a constant second derivative. So it seems like our quadratic function x squared equals y has a constant second derivative of 2. But y doesn't have a constant second derivative of 2. And will this be true for all quadratics? I'm not going to give you a rigorous algebraic proof. I'm going to give you more of a common sense visual proof, and hopefully that will satisfy you. And this proof hangs on the fact that we can see this function as basically a series of squares. And if you think about it, this table could represent how the area of a square changes when the side length of that square changes. When we have a square with sides of length 1, the area is 1. When we have a square with sides of length 2, the area is 4, and so on. That means this series of squares I just drew with increasing side lengths is actually just another way to represent the function x squared equals y, where x is the side length of the square, and y is the area of each square. So to answer the question, why does x squared equals y have a constant second derivative, we can start by looking at the way that the areas of these squares grow when the side length grows. When we go from x equals 1 to x equals 2, we're adding 3 tiles onto the square. We had 2 on the corners and 1 on the end. So that's a plus 3. When we go from a square of 2 by 2 to a 3 by 3 square, we still add these tiles on the corners, and we still add this tile on the end, but we're adding 2 more new tiles. And they come off of the one at the end. So we're adding 5 total. And then over here, well, we still add these 2 tiles, and we still add these 2 tiles, and we still have the tile at the end, but we're adding 2 more that come off the one we added at the end before, so that's 7. And what we can think of it as is every time we add 1 at the end, it kind of spawns 2 more. We added this one on the end, and then we had to add 1 below it, and 1 to the right. We added this one at the end, and then we had to add 1 below it, and 1 to the right. And hopefully you can see how this would just keep going on and on. Each time, we would have to add 2 more than the last time. And so that's kind of a visual proof that y equals x squared has a constant second derivative of 2. Now that we've proved that y equals x squared has a constant second derivative, let's try to prove it for all quadratics. So the key here is to realize that just like I could write x squared equals y as a series of shapes, I can actually represent any quadratic equation as a series of shapes. And so I would like you to pause and just take a moment to think about how you would draw out 3x squared plus 5x plus 2. So 3x squared, well, that's the same as the area of 3 squares with side length x. 3 squares with side length x. And then the 5x, well, that's the same as a shape, the area of a shape that's 5 by x. That area is going to be 5 times x, or 5x. And then this 2, well, we can just represent that as a 1 by 2 rectangle. And more generally, if we think about the definition of a quadratic, which is an equation of the form ax squared plus bx plus c equals y, well, this ax squared term, that's just the same as the area of a squares of side length x. This term, that's just the same as the area of a b by x rectangle. And this term, well, that's basically the same as the area of a 1 by c rectangle. Now, what we want to show is when x is increased, this whole thing still has a constant second derivative. So let's look at how each of these terms is growing when x increases. Well, we already looked at how squares grow when x is increased. And we know that every time we increase x by 1, we have to add 2 more to the area than we did the last time. That's why x squared has a second derivative of 2, is because we're adding 2 squares more than we did the last time each time. So if we have a squares, then we're going to add 2a more each time than we did the last time, because we'll be adding 2 more for every square. So 2a, that would be our second derivative. Now let's look at how bx grows. So to investigate that, I'm going to make a little table here. When x equals 1, we would have a 1 by b square, 1 by b. So if b was 3, we would have 3 squares. If b was 4, we would have 4 squares. When x equals 2, well, then we'd have a b by 2. So the area of this is b, the area of this is 2b. Put area, side length. When x equals 3, well, then we're going to have b by 3. So the area there is 3b. So at this point, we can kind of just see that we're adding another row of b every time we increase x by 1. So this thing is growing by b. So if this were 3, we'd be adding 3 every time to the area. If b were 4, we'd be adding 4 every time to the area. And this doesn't really have a second derivative. The first derivative, the rate of change, is b, but we're not adding any more this time than we did this time, or any less. So for this term, for the bx term, 0 is our second derivative. For c, well, that's always just c. When x is 1,000, we add c. When x is 0, we add c. So c never changes at all. So its first derivative is 0 and its second derivative is 0. So if we look at how this whole thing is changing, the second derivative of this term is 2a, the second derivative of this term is 0, and the second derivative of this term is 0. So overall, the second derivative of any quadratic is 2a. And this is something that you might learn in calculus. You might learn something called the power rule, where you take this exponent and you bring it down and you multiply it by a, and you get the second derivative. But here, we just proved it using squares and rectangles. So that is the intuitive visual proof of why the second derivative of any quadratic is 2a.